Okay, so let us start with we completed this particular portion that how the horizontal force appears. We had understanding that on any face of wall, I can find the horizontal force using integration also. There is one more method to find it, and yeah, the particular using the understanding of projected area, we can still do that question in a very easy way. Okay, so what we are going to do is establish this relation and have a greater understanding in a much more great way. Okay, now try to see. Let's suppose I have once again a cuboid kind of geometry. Okay, 1 minute. And then what I did was I filled up this particular container with two kinds of a liquid. Okay, one liquid having density rho, another liquid having density 2 rho. Got it? So this is the separation. This is rho and this is twice of rho. Are you able to get me or not? And base length, this length is A. Okay, so the numbers are, this is A, this is B. Okay, let me just draw it over here. This is B, and this is also length L. Means from here to here, this is length L, and from here to here, length L. Find the force on the wall. Find A, no, A, B, C, D. Find the force on the wall A, B, C, D. Okay. I don't get this to be perfect. Okay. Uh-huh. Think once again and then reply. Okay. Find the force on the wall A, B, C, D. Now, see, there are, if you look over here, then since the density is varying, I'll have two different projected areas or not. If you look into the configuration, I have two different projected areas. One area which consists the liquid, like one area which has the liquid rho, another area which has the liquid twice of rho. Are you able to get me or not? Isn't it? So this is liquid rho and this is liquid twice rho. Okay, now if you look into this length is L, this length is B, and this length is also L. So if I just try to draw the force, then the force will be present for two different surfaces. Okay, one will be at this center, another one will be at this center. I'll have two different center of mass or center of buoyancy or sorry, center of application of force or not. Yes. So for first one, F1, which I call it, this is what simple formula. What is the center of pressure at the center of projected area? So pressure at the center of projected area is rho g L by 2, isn't it? Into the area L into B. Are you able to get me on that? Yeah. So this is F1. What is F2 then? F2, if you measure the pressure, means wait. If you measure the pressure is due to this liquid level and this liquid level, both of the liquid levels are not. How come thrice? How come thrice? One has twice rho density and another has a rho density. So how come you can add them? Okay. Acha, you were saying thrice of rho GL. Ah, okay, that is correct then. So for a whole first liquid, it is rho GL plus the second liquid twice rho G, but till L by 2 only, isn't it? Into the area L V. Yeah, so therefore total force on wall. Yeah, just F1 plus F2. How much it is? Is it in consideration of this projected area or not? So this is why I told you this relation. So this is 5G L square B. Uh, 1 minute. I think I forgot one more quantity. 5 rho GL 5 rho GL by 2 and then area L into B. Are you able to get me or not? That's my total force on the wall AB, isn't it? Are you able to get me? No problem till now? Okay, now let us consider one more problem. Let's suppose now let us move to the different geometrical configurations. Now I'm moving to the you can say that different kinds of geometrical configurations. So let's suppose if I have frustum, like frustum means the geometrical, yeah, the geometrical figure of bucket is called by a name frustum. Okay. 1 minute. The geometrical figure of bucket is called as frustum. Is that clear? So let's suppose I fill up this frustum in this bucket with the water till horizontal level. White or not? So the point is, let us see what is given. They are saying that the base radius is r and more top radius is 2r. If this is yeah, this is 2r. Are you able to get me or not? And the height of this frustum is also given to you. That is h. That is how much h, and the density of liquid utilized is also given, which is rho, which is rho. Okay, so First question: force exerted by liquid on bottom surface of wall. Force exerted by liquid on bottom surface. And then second thing is, second question, compare. I call this bottom surface force as F1. Okay, so compare F1 and weight of liquid. Third, find force F2 exerted on exerted by liquid on the walls of vessel. हाँ, बताओ. I'll give you a hint. This For these kind of objects, the volume of frustum is given as 1 by 3 pi h. Okay, r1 square plus r2 square means outer radius plus inner radius square plus r1 r2. So this is just like a cone. If you see the volume of cone, yeah. So volume of cone is what? 1 by 3 pi r square h, isn't it? But R here is a subtraction of R1, means you will have to find the full volume with respect to 2R, and then R1 and R2, then subtract it, you will get the same result, R1 square plus R2 square plus twice R1 R2. Sorry, R1 R2. Is that clear or not? So this is why I'm asking you that find the F1, weight, and all those questions. Okay. Do it just 1 minute. Just laptop down. Is it done? I'm just talking about the whole curved surface area. I'm not talking about one wall. I'm just talking about whole curved surface area. Tell me. Okay. If I just want to find the volume first, volume will be what? 1 by 3 pi h r square 4r square plus 2r square. That is equal to, that means volume is equal to 7 by 3 pi h r square. ये होगा ना? Hmm? Now, if I know my volume, then I know my weight. Weight is equal to density into volume. So, how come you have to check that? You do not know still. You do not know still. So, rho is equal to weight is equal to density into volume. So, density into volume is how much? That is 7 by 3 pi r square h into rho. That's my weight. Are you able to get me or not? Acha, force at the bottom is nothing but my pressure at the bottom into area bottom. Yes, what is pressure at bottom? Rho gh into pi r square. So, so if you look over here, if you just try to see this equation, acha, here density into volume. Where is gravity? I am looking. Sorry. Weight is equal to, this is mass into gravity g also now. Weight is equal to mg. Okay. So look over here. You see that this is, if you look into the weight one, that is 7 by 3 pi r square rho g. है ना? So if I want to write in terms of that, is 7 by 3 is almost how much? 3 to the 6, 2.33 something, isn't it? 2.33 rho g h into pi r square. This is my weight. What is my force at the bottom? Just rho g h into pi r square or not. So what do you observe? That force of bottom is not similar to weight, but less than the weight. But less than the weight. That is why in older days you see the bucket was made of this shape, because they were aware that whatever weight they are lifting is not same as the weight of the liquid. It is actually less, so they have to apply less force to lift it up. Are you able to get me? But nowadays you see people make perfectly horizontal means with the same whatever is the upper cross section, they make the same cross section at the bottom. But those buckets are not going to be present for a longer duration of time, which will means it will definitely penetrate the bucket from the below. Are you able to get me? Is that clear? Now they are asking that find the force on the curved surface area, isn't it? So how to find it? Any idea? No, there is. If you find with a normal way, it's going to take a lot of time. No. See, this is my bucket. This is my bucket, isn't it? Now, whatever force, 1 minute, whatever force is applied at the bottom. Okay, so there is a force at the bottom or not? So that basically, you know that the liquid will also apply the forces. So this is force from the bottom. I call it as F1. F1 is the force from bottom. Okay. So liquid also applies, means the container will apply the force from each and every side or similarly F2, similarly from this. And F2 is the curved surface force. Now the curved surface force is similar. So at any point, I'm considering there are many lot of curved surfaces force, which I call it as F2. Are you able to get me or not? Now, as you try to see that these F2s, since the volume is totally different, means volume is increasing as I'm moving upwards. So the net resultant of this F2 will be also upward, isn't it? At the center of the mass of the liquid. So these F2s are also going to be resultantly upwards. Are you able to get me? Now you know that these forces must balance my weight of the liquid, then only the whole liquid will be at rest. Are you able to get me? So this is why F2 can be calculated very easily. It is mg minus F1. But what is mg? Rho means mg is just the weight, which is 7 by 3 pi r square h into rho g minus F1 rho gh pi r square. So this implies F2 appears as 4 by 3 pi r square h rho g. This is my net force F2. Is this clear? Yeah, you do not have to find out, but they want a trick for this. It's simple. It's a very simple trick. Whenever you get this, see that there is a trick to find. Okay, let's suppose in this bucket I filled up. Okay, I filled up the liquid. Now, whenever you see this kind of geometries, conical or something like that, then instantly draw a cylinder in it with the ends. Okay, what you draw? You draw a cylinder. Okay, so you look over there. The radius of the cylinder exactly matches with the bottom. Okay, yes, isn't it? This is upward was 2r, but bottom was r or not. Okay, so basically the force, vertical force by the wall, vertical force by the wall, not the bottom force. I'm just asking vertical force means the net resultant vertical force due to this wall F2 is simply nothing but uh, weight of liquid minus extra or my you can say simply weight of liquid. No, you can, but that is a rude argument. It's better to give the perfect argument. It's just the weight extra present. Ah, that's a perfect statement. Excess weight present outside the cylinder. Excess weight present because see what will happen. These forces F2 will each were present in each and every direction and they will cancel each other or not. So how the force is present? It is present due to these water molecules which are applying the force like this way. Ha. So that is why the force is only present on the curved surface of the container for the weight which is extra present outside the cylinder. Because net curved surface force is getting, we can easily calculate through projected area which will cancel each other. Is that clear or not? Alright. So this is why the net resultant of all these forces just upward vertical force F2. Are able to get me or not? And that is why we are just finding the extra weight which is present outside the cylinder, because the weight inside the cylinder will balance each other. So the excess weight which is present outside the cylinder, that will only apply the force F2. Is that clear or not? And that is the, yeah, excess water, excess extra water which is present outside the cylinder. Okay. Yeah. So that F2 will be how much? Simple. Total volume of the frustum, total, you can say, total weight mg of the frustum minus weight inside cylinder, isn't it? So F2 is equal to mg of frustum is 7 by 3 pi r square h rho g minus weight of cylinder is just volume of it, which is pi r square h into rho into g. So if you just calculate it, this is also 4 by 3 pi r. So this you can apply to understand the concept in a much more greater sense. Are you able to get me or not? Okay, can we move ahead? Okay, now look over here. Now let us just take an argument. I have three different kinds of buckets. Okay, and their vertical height is same for all of these buckets. Their vertical height is perfectly matching with each other. But in all of them, they are arranged in a different way. Got it? Yeah, weird way. Now, each one is filled up with a liquid of density rho. Okay, all of them are filled up with liquid of density rho. Question is, if this is first vessel, second vessel, third vessel, then question is, if the force exerted force exerted at the bottom is F, and weight of liquid is W. ठीक है? Weight of liquid is W. ठीक. Then if the height is same, then compare their, if height is same, then compare their, what is they are asking? Compare their force versus weight. Then compare F and W if height of vessels are same. Now, and this thing which we are studying right now, yeah, we call it as hydrostatic paradox. बताओ क्या हो। जल्दी से बताओ। I'm completing every type of problem for you. This fluid mechanics can take a little bit of time, but it is going to be a awesome concept, isn't it? Acha, look over here. If I just take the first vessel, isn't it? So what? There is nothing to call about radius or something. Just we will think. Just draw these cylinders. Remember that. Draw these cylinders always for these kind of questions. Okay. So look over here. See that. Here we know that in first case it's a very thing. First case, what happens? Weight in one will be greater than force in one or not. Force at the bottom. Right now we derived it, isn't it? Yes. So weight will be always greater in one. This is my first vessel. Vessel. Are you able to get me or not? Is this clear? Next thing, in second case, you will find out that the force of bottom is exactly matching. Why it is matching? Force at the bottom in second phase. Yeah, because both are same. So basically, net force is how much? Zero. Net force is how much? Are you able to get me or not? So yeah. So yeah. So here we can write the force due to side wall in first case. Force due to side wall in one is nothing but mg minus f1. Are you able to get me or not? Yeah, which is simply weight 1 minus f1. Are you able to get me? Here f2 weight and f2 are same. So look over there. That's why I told you at that time that force due to side wall in case of perfect cylinder is how much? Zero. Because weight is exactly equal to bottom force. Are you able to get me or not? Is that clear? Third case, what happens? Now, if you look into the third case, that's a geometrical. If you see that the volume of cylinder is more, isn't it? Yes. So this is why what actually happens is the weight it becomes this time uh, weight third becomes less than force at the bottom. Are you able to get me or not? या सो अगर मान लो जैसे समझना मतलब force at the bottom is more means this force the force at bottom f3 is very more than the weight of the body itself. Are you able to get me or not? So these kind of this is why we use the conical flasks in titration and all when we apply when we want to apply some extra forces. Are you able to get me? So look over here. Here also I'll get the force due to side wall, and that is weight. I'll just write this as F3 force bottom minus weight bottom, but this is in downward direction. Which direction? Downward. Yeah. Means so basically F2 over here is upwards Sorry. 1 minute. Let me just draw. That is force due to side wall is upwards and force due to bottom is bottom. Force due to side wall over here is nothing. Force due to side wall is 0. And here force due to side wall is also downwards. And that is F3 minus W3. Are you able to get me or not? Okay, and this is why we call it as hydrostatic paradox. Means the weight feels different in different types of geometrical objects. Okay, is this clear? So this was all about the pressure, force, and all this kind of calculations. Now we are going to understand that how to measure this pressure. To measure this pressure, we utilize a object which we call it as baro, yeah, barometer. Are you able to get me or not? And this barometer helps us to measure the atmospheric pressure or something like that. So barometer, it is a device to measure atmospheric pressure. Okay, is that clear? How does it measures it? Let us see that. So what they do, they take the water level in, मान लो जैसे बारिश वारिश हुआ तो बारिश की पानी एक जगह अपन ने इकट्ठा कर दिया. ओके, and no, means just we take a container or a bowl and then we'll fill up that with liquid or water. Okay, now then we'll take a capillary tube and we'll take a particular kind of capillary tube and we'll insert this capillary tube inside this water which is vacuum in nature. कैसा nature रहेगा उसका? Okay, now if you will see that since it is vacuum, so the pressure inside is like, look over here. If this liquid column is in contact with the air, it has atmospheric pressure P naught, isn't it? And here vacuum is there, so pressure is 0. So water will start rising up over here, isn't it? Yeah, so water actually rises up till some level. Okay, water rises up till some level. And here actually the pressure is 0. Pressure is how much? 0. And this water rises till the height of how much? H. Let's suppose this water rises up to height how much? H. Then we can directly write the formula of particular atmospheric pressure now, because here it is P naught and here it is 0. So P naught minus 0 is equal to rho GH, where rho is the density of liquid. Yeah, simple. So P naught, we got the formula that atmospheric pressure is nothing but rho g h, where h is the height of liquid raised, isn't it? Are you able to get me? Now, basically, you can find easily. So if I just look into different heights and all, let's suppose if I want to find that how much height is raised due to atmospheric pressure of any liquid, so that height can be written as simple atmospheric pressure divided by rho g, isn't it? Yes. So now look over here. Let's suppose let us design some barometer. So first barometer we call it as, Done. Yeah. So let's suppose if I design mercury barometer. Okay. So that means the liquid which is kept over here, see that this height of the liquid column which it is rising up is dependent upon the density of the liquid also or not? Yes. So let's suppose if I take the liquid to be mercury, so mercury density is almost equal to 13.6 13.6 gram per centimeter cube, which can be, okay, let us not convert into kg, it's your task, not mine. And g is equal to, we can take 9.8 atmospheric pressure, you know that it is 1.01 into 10 to the power of 5 pascals, isn't it? Yeah, so this is my different quantities. When we put these values in the height of barometer, so height of mercury raised, you will find out that it is exactly equal to something, it will appears as 76 centimeter. कितना height raise up दिखा हुआ मिलेगा? Yeah. Now similarly, let's suppose if I just keep a water barometer. So look over here. Its density is 1 point or 104 gram centimeter cube. G here 9.8. Atmospheric pressure is still same, which is 1.01 into 10. So when I will put it, you will find that the height of water raised is going to appear as 10.8 meters. So look over here. If I want to measure the atmospheric pressure, there should be a perfect selection of liquids also. Because if I select the liquids which have less density, they will basically have much more height as compared to the mercury. So basically, mercury was chosen to be the finest barometer consideration because its height can be only raised till how much? 76 centimeter. Is that clear or not? And next thing is, mercury will not stick to the glasses of the capillary tube, while other barometer, other liquids can still means they can. Yeah, water definitely sticks to the glass. We'll tell you, we'll come on that. But mercury never sticks to it. Are you able to get me or not? So this is why height of the mercury raised is how much? 76 centimeter. And this is why we define, since the atmospheric pressure is such a big quantity, we, to make our calculations very easy, we define 1 atm pressure as pascals, which was the original unit, as just 76 centimeter of Hg, to make our calculations very easy and useful. Are you able to get me or not? So one, that is why one atmospheric pressure is defined as 76 centimeter of Hg. Okay. Now let us define most important thing, and the problem is this, and we call this as faulty barometer. Okay, now look over here. So what is the condition? Simple condition is there. Once again, if I have, let's suppose, any liquid surface, okay, which has density rho, and I dip a barometer in that, but this time the barometer is not vacuum. It has a gas. It has a gas. Wait. So what happens? Atmospheric pressure is going to be P naught, isn't it? This liquid is in contact with the air, but here So this liquid rises up this time a little bit less, like previously it used to rise up more, but this time it is going to rise up less because at the top the pressure is not zero, isn't it? So let's suppose in top there is air which is present. So there will be another pressure P which will be present over there. Are you able to get me or not? So the equation will appear at P naught minus P. And if the height raised in this faulty barometer is H, then P naught minus P is equal to rho G H. And atmospheric pressure is this time given as P plus rho G H. Are you able to get me or not? Is that clear? So pressure gets added. लिखो जल्दी से फिर अपन आगे बढ़ेंगे. Okay. Now the question arises over here. The biggest question arises, which appears is, uh, what is this? What happens means if this liquid column is rising up, it's compressing the air or what? When water rises, simple when liquid rises, compresses air, isn't it? So due to the compression, the internal energy of the air molecule will increase. But that actually does not happen. What actually happens is we consider that this compression of air, okay, means you can write this statement that generally the expansion and compression of air inside these barometers uh, or gas, you can say, not air only, is an isothermal process which was proposed by Newton. Okay, it's a which kind of process? Isothermal process, but only on certain condition when this gas or when you can say when the gas remains in contact with liquid surface. Is that clear? So whenever there is a compression of gas or expansion of a gas, when there is a contact with the liquid surface itself, then only it is going to be isothermal process. If there is just gas inside a container, sorry, that's not going to be your isothermal process. Is that clear or not? So if it is isothermal process, then P1 V1 is going to be directly equal to P2 V2. Can I just apply this formula? And this actually provides us the understanding how to find this P value from P1 V1 and P2 V2. Is that clear or not? Let us solve one question regarding that. Let's suppose first, 1 minute. I had one barometer which was upside down and then I inverted it. Okay, means I just inverted it. You can say previously I had the mercury trapped. Okay, this is my mercury which is trapped over here. Okay, and that mercury is still trapped of same length inside that tube. Okay, yes, is that clear? Now look over here. this column, which was way up of the mercury, okay, this column was 43 centimeters and this was of air. क्या चीज का था? Air. And this column was of mercury Hg, which was of 10 centimeter. When I inverted it, the mercury still remains the same, which is of 10 centimeter. Okay, but the air column changes. So your task is, if I just invert it, then what is this length of the air column left out right now? I call it as means previously it was 43. Now what is this air column, you have to tell me. If I just invert it, yeah, do it 1 minute. Is it done? You can consider this as initial state. This is the final state. Yeah, you have to use P1 V1 is equal to P2 V2. You have to use that statement of P1 V1, P2 V2. Okay. Should I solve? So if you use over here atmospheric pressure, so it becomes a tedious task. So let us see that. Acha, here, even if it is, listen, even if it is inverted, air will be over here. So pressure over here will be how much? P naught. Similarly, air will be over here also. Here also the pressure will be how much? P naught. Let us just understand that at the interface over here, the pressure was P1, and here the pressure becomes how much? P2. Pressure becomes P2. Then, and if I just consider that if we know that at air liquid interface, which kind of process is there? Isothermal process is there, isn't it? So if isothermal process is present, then P1 V1 is equal to P2 V2, isn't it? And if P1 V1 is equal to P2 V2, that is only possible if I can write it as if I can write the pressure equations. So the question arises that what is this P1? So you only tell me. Here the pressure will be higher and here the pressure will be less or not? Yes. So when I'm going upwards, so when let's suppose if I want to find P1, P1 will be what? Nothing but P naught means down pressure P naught minus rho GH of my HG column, isn't it? Yes. Well, P2 will be what? P2 will increase this time because of the HG column. P naught of HG column, isn't it? So if I want find P1, it's since we are doing the calculation, as we know that we can do the calculation in very easy way because I can just write, we can write the P naught in terms of the height of Mercury or not. And here Mercury is also given, so utilize that concept. P naught is just 76 centimeter of Hg and rho GH is just 10 centimeter of Hg, isn't it? So the P1 pressure is how much? 66 centimeter of Hg. Similarly, P2 pressure 76 centimeter of Hg atmospheric pressure plus extra 10 centimeter of Hg 86 centimeter of Hg. Now, what is the formula of isothermal process? P1 V1 is equal to P2 V2. What is P1? 66. And what is volume? Simple volume of the air column. Volume of the air column I have to take, isn't it? So that volume is what? Area of cross section A into volume A. Length is 43 centimeter is equal to P2. P2 is 86 centimeter of Hg and all are in centimeters, so no need to tension also. Volume area of cross section still remains same, but the length is x this time. So x is how much? Simple 66 into 43 divided by 86, which comes as, if you find out, this comes as almost 33 centimeter. That's your answer. Got it? 43 2s are 86 and that is 30. Are you able to get me or not? Okay. So this was the concept about our barometers, different kinds of vessels and all. One more question we'll do of barometers. Let us see it. Okay. बोल रहा है there is a long tube. Okay. Long tube opened at both ends is dipped in mercury Uh, okay, such that its length outside the Mercury is 4 centimeter. Okay. Now upper end of tube is closed. Now upper end of tube is closed. Then tube gets shifted vertically by 16 centimeter. Okay. Then question is find the final length of air column. Find the final length of air column. Can you do it? Yeah, density is true. There is no such question of density over here. If you think, draw the diagram first, then only you will be able to do. Uh-huh. हाँ, बताता हूँ। Let me देखो, समझो अच्छे से. What it is saying that I had the liquid surface. Okay, I had the liquid surface. Now, in this liquid surface, I put it a barometer. Okay, so this barometer was too much down and just 4 centimeter was upwards. Okay, but this is the open end. Sorry, 1 minute. This is when it's open. Yeah, so both are open ends, and it is how much? Uh, 4 centimeter upwards, isn't it? Now, when I just close it, it gets shifted, and it gets shifted by this is 4 centimeter, and this got shifted by 16 centimeters. Okay, but the point is the liquid rises in this. Okay, the liquid will rise over here or not? So if you can find the length till which the liquid is rising, you have to find what? So the gap, it's telling to find the gap of the air column. So you can directly find it is to be 16 minus x or not. So the gap of air column is simple, 16 minus x, isn't it? So sorry, 1 minute. Yes, this is going to be 60. Initially it was 4, and then it is shifted by 16. So total length it got shifted 20. Okay, this is 20 centimeters. So this is 20 minus x. Find the next. Okay. Yeah. Do it. What? Is it done? ओके should I do? अब ध्यान से कैसे करते हैं. Okay, now look over here. See this. So first important thing, we know that whatever happens, this liquid air interface goes through isothermal process. So P1 V1 will be equal to P2 V2, isn't it? Yes. अच्छा. अब ध्यान से देखो. Initially air was present over here also, isn't it? So P1 is what? It has direct atmospheric pressure P naught, isn't it? So pressure is P naught 76 centimeter of Hg into volume 1 which is 4 centimeter into area of cross section है. यही होगा ना. Yes. Now here then what will happen, you will see that now what is happening as look over there. So when this air column rises, so initial pressure is P naught, but here the pressure is P dash, isn't it? Yes. So pressure will be what? Simply it will be 76, and this is if this is mercury, if this liquid is mercury itself, okay, it is given that it is mercury, then yeah, then it should be equal to P naught, which is 76 centimeter of Hg minus X centimeter of Hg, isn't it? That's my pressure P2. This is my pressure P2, isn't it? Into volume. Volume is area of cross section A into the particular air column, which is 20 minus X. So what I am going to get? 76 into 4 centimeter of which is centimeter of which is common and got cancelled out. Area cancelled out. It is equal to 76 minus X into 20 minus X. So can you just solve this or not? This is, you are going to get a quadratic equation over here, isn't it? So if you will solve this quadratic equation, X will appear as 80 centimeter and 15 centimeter. Now look over here. So 80 centimeter is even not possible. The pressure cannot be more than, so which if X, yeah, so X length is just 15 centimeter, and you will find out that this particular length of air column then is just simply 20 minus 15, which is 5 centimeter. Are you able to get me? So this was all about your barometers and all. Tomorrow we'll start with Archimedes principle, problems related to that. Okay, we did some problems, but once again we have to do. There are a lot of questions which I need to do from Archimedes principle. There are still many concepts, center of buoyancy and all those kind of things. Then different kinds of flows. उसके बाद Bernoulli's principle, and then we'll move ahead. Bernoulli's principle questions, and then we'll move ahead. Okay. The surface tension. Acha, one thing is there. Uh, at the end, the surface tension I have taught, like it will be a time saving thing for you, isn't it? See, I have taught this surface tension. I have recorded this video. Okay, like over here, it's in my laptop, and I'll start uploading it. So, if you just at the end, 1 minute, let me